Everyone, March 11th. All right, let's do this. Remove zero sum consecutive nodes from linked list. Given head of a linked list, we repeatedly delete consecutive sequences of nodes that sum to zero until there are no such sequences. After doing so, return the head of the final linked list. You may return any such answer. Note that in the example below, all sequences are serializations for this node. Yeah, so it's not a list. It's not an array. It's actually a linked list, right? So what does it mean? Repeatedly delete consecutive sequences of nodes. So we're given a head. So in this case, we first delete what? -3 and 3? I'll put 3 and 1. 1, 2, 1 will also be. Oh, repeatedly delete consecutive sequences of nodes that sum up to 0. These three sum up to 0 as well. I see. Okay. So we need to 1 to 1000, which means we can afford to do. So we just need to remove everything. So the final result is that there is nothing sum up to 0. That is the final result. So we can just go from start and then we just keep adding. Yeah, we can keep adding, and how do we detect when when something added to 0? Well, if we add, and then we add something, and it becomes the same, and we're talking about prefix sum, right? If we have prefix sum, and as we add something that has the sum that has shown up before show up again, that means we have encountered a sequence with the sum equal to 0, right? So in this case, we can actually do this example. This is actually a good example, right? We have 1, 2, 3, -3, 4. If we do prefix sum, we have 1, 3, 6, 3 again. So this one has shown up before. This means if I record, actually don't need to record. I need to record I do have to record. I have to record this node, right? We have to record this node. And we're actually gonna put a dummy here. So we're going dummy, and then head, and then node, right? And then in prefix sum, dummy is gonna be 0. Head is gonna be whatever head dot value. This is 1, this is 3, right? And this node is gonna be 6. Next node is gonna be 3 again, and then boom, I had 3 before, right? So basically we're gonna look into because only 1000 nodes, so we can have an array, right? We have an array, and every value in the array is -1. Okay, and then when we hit this, and if any value, yeah, and then this value, if we have hit it before, I will actually no, it's not. It's gonna be an array of list node. Okay, it's gonna be an array of list node. Okay, array of list node, and we're gonna set everything to null. Okay, everything is null, and then once 1 hit, I put 1 as the node. 3 hit, we put a node, and if this and this it exists, right? It exists. It's not a null. That means it exists. That means we need to remove a sequence, because this add up here and add up here, which means this is the sequence we need to remove. So it's this node need to link to this node's next, right? This node's next. And then once we're done, right? Once we're done, we will once we done, how we gonna, everything in here needs to be removed, right? We can that is a good point. How do we handle that? I mean, we can just go back, right? We can just go back. What do you mean by go back? Because I need to remove the things that are already, because I want to restart, right? I want to restart. How do I restart? I mean, I already have whatever it is, so I can start, but in this whole stretch, how can we remove this whole stretch? That's a good question. How do we remove this whole stretch? Yeah, I mean, remove the nodes is easy, but how do we remove the stretch? Remove the stretch. I mean, we can do, a stack, okay? Which just means in the stack, it will also push these values. We'll push these values in the stack. Yeah, we have a prefix sum. We have this prefix sum, and then we need to pop. How many nodes do we need to pop? Right? How many nodes do we need to pop? Okay, so what you're saying is, once we hit someone that has it before, then we stop popping. Okay, we pop this, right? We'll pop this, and then we'll set. Now we first remove the linked list, okay, because that's just one move. It's easy to do, and then the node will become. Put a node on the next node, and then every time we will pop this, and each time we pop, this one will reset to null, right? We'll reset it to null. We'll reset to null, which means this value has not been done before. But you might as well just use. No, we do need to use this. We need to use it because we need to know which node it is. Which node it is. Maybe, yeah, maybe you should just use a stack for, use a stack for this. We use a set for the values, and it will use a stack for a list node. How about that? Right, and then we just keep popping until we find the next one that is 3. Okay. Yeah, we just keep popping. Right, we keep popping. And then initially we're gonna have, but then we don't know which one this is, which is fine, right? Which is fine. We know the current node, right? We know the current node that will lead it to 3, right? We know this node. We save it separately. Okay, but this one we didn't even push into the stack. Then we start popping on the stack until we find the same value. Now that is the node of interest, right? And then we can just do the link, and every time we pop, it's removed from the set. Okay, I think it's doable, and I'll even say every node will be visited only at most twice, right? At most twice. Okay, let's do this. This is 12. Well, I might just do the whole thing. Ooh. Oh. All right. So what do we need? We need can we have a stack? Yes, can we have a stack of list node? We'll call it stack, new, array list, or a stack. Oh, it is a stack. Okay. Can we have a set of integer as well? We say scene. That's gonna be a hash set. Okay. And then we have a dummy. We can say list node dummy equals to new list node. Oh, that's not what we want. Oh, no. Redo. We just don't need a list. This should be list node. And next shall equal to int val. I probably have to do val equal. Not val equal. It's just gonna be doesn't really matter what value. We can put a 0. But next shall be head. Okay. Okay, now we have dummy. And then stack will dot add dummy. Alright. This is the start dummy should put in there. And then scene dot add 0. Okay, now we'll do prefix sum. Okay, so how do we do prefix sum? Well, we say node equal to head. What is node? Node is a list node. Okay, now we say while node is not equal to null. We can just say while node. Okay. While node. Oh, I also need to know the value, right? It's just not just seen, because when you pop, you also need to know. Oh my goodness, it's not just a stack. All right. Do we need a stack? What do we want to know? Right? It's not a stack, because you're just popping back now. We don't need a stack. What we want is just, I think it's just integer. I think integer will be fine. Okay. I think integer will be fine. So we do need a dummy, and we do need a stack and a scene. Okay. And we do need a dummy. And then, but then how do you know which one's which? Yeah. How do you know which one's which? So you're telling me that I need 2 stacks. One for the list node. One for the no. I still think stack is for this, and prefix sum is just gonna be a prefix sum. Stack this, we can say list integer, right? Pre-sum, okay, new array list. Okay, this, and then pre-sum dot add 0 as well. Okay. So now we're gonna start while node. So we can say current sum shall equal to presum dot get presum dot size -1. They don't have another one for this? Dot peak? They don't have peak. I mean, it could be a stack as well. Actually, we don't have to use a list. I don't need a list. We just like to stack, right? I think this can be a stack as well. Right, and then I probably can do, let's see, can we have another one like say peak? Top of the stack without removing, yeah. So current sum is dot peak plus no dot val, right? And then we say if scene dot contains current sum. Okay, so that is the case where we need to do something. Okay, it contains, so we need to start popping. Right, we need to start popping. Then we say while while presum dot peak is not equal to current sum. Okay, then presum we're gonna say presum dot pop and stack dot pop as well. So we pop both, right? So we need to find the one where the presum peak is equal to current sum. Okay, so now we have the presum peak is equal to current sum. Now that is the target node, which is in the stack. Now what we can do is we say stack dot peak. Okay, stack dot peak is the node itself. Dot next shall equal to the current one we need to escape. Right, we don't use the current one, so node dot next. Right, this would escape everything. And once we've done that, node equal to node.next, right? We go next. And everything else has been removed. Oh, and everything along the way needs to be removed from scene as well. Ooh. So what we need to do is scene.remove. Oh my god. Wow, those scenes look great. Scene.remove presum.pop. Okay? We do presum.pop. So not only pop this, we also remove from scene. And then blah blah blah, we handle everything. Then we do this, done. Else, if we have never seen it before, okay, that's a new sum, right? That's the current sum is good. So if that's the case, then we need to do a few things. First, scene.add current sum, and then presum.add current sum, right? And then stack.add node, and then we do no equal to node.next. Right? Now we do no equal to node.next. And then we keep going through this until we hit the end. And then when we hit the end, what we're going to return is dummy.next. Okay, so what is this problem? 1171. So use stack. I think this is an ON. We'll see. We'll see if I got this one right. All right, we try some of these, and of course we should also try. There's an edge case, another edge case. Maybe we can do another edge case. Bless you. Oh, and this edge case. How about this edge case? And how about this edge case? All right. Or blast through a couple of edge cases and see. Okay, I cannot do that. I have to say, well, node is not equal to no, pretty much. Cannot convert it. Yeah, that was Python. You can do it. All right. I think this one looks promising. We're gonna give this a shot. Oh, we've done this before. And we've done this many times. And this one is slow. Okay. This is ON, but we have to run it twice. Right, I agree. We run it twice. All right, so what are the faster methods? I mean, we can just get the value out. If we get a value out, then we don't have to go through this. Okay, we can try that. We get the value out. It's like another method which it's creating in place. No, not creating. It's creating new, right? We're creating everything anew. I just want to see if it's gonna be faster. So this is basically. Okay, this method we say create a new array from scratch. Okay, so there's no stack, no nothing. All we do here is going to be we just produce the thing first. Right. Okay. We say list integer vals goes to new array list. Okay. And yeah, but you still have to go through it twice because it's. How do you know if it's not seen before? Right? Yeah, how do you know that it has not happened before? You don't. But maybe because the size is 1000, maybe ON squared is actually fast. Like seriously, ON squared might be fast. And because it says it has most 1000 nodes. Okay? Which means we probably can do it this way. We can say int, right? We can say int presum new int 1000. That's it. Because that's at most 1000. I mean, if you want, you can say 1001, but I don't really think it's necessary. And maybe we should do 1001. Right, 1001. And we can just say node equals a head, right? Node equal to head, and we have an index. Okay, so this we add before, we put it in, put in. Each time we add, we check if it's seen before. If it's seen before, we will do yeah. So basically, we will say for I. Nah, we can just say int I equal to 0 while yeah, I don't really care, right? While head, we can just do head is not equal to null. I don't even care because I'm gonna create something from scratch anyway. And then we just say int current equal to actually that shouldn't be, that should be 1, right? Shall equal to head.val plus presum I minus 1, right? And then we say for int j is 0, j is I minus 1, j larger equal to 0, j minus minus, okay? And we say if presum j, okay, is equal to current, what do? If j is equal to current, and then we reset the position for I, right? We reset the position for I. So we say I is equal to, I shall equal to j plus 1, right? And that will break. I will break, right? So this one, basically we update the value for I. And once this is done, I point into the next position. And if we don't find anything, then we need to update the current I, right? Update the current I, because the I is pointing to the new one that we haven't done yet, right? I is pointing to the value that we have not been handled yet, right? Have not been handled yet. So yeah. So once we're done with this, we basically are going to but do we do the current? If the current is equal to a previous one, then we shouldn't, right? Then we should not. We should have a sentinel, right? We should have a boolean called sentinel is false, and once it's hit, sentinel equal to true, right? So once we get out, we can check the sentinel. If sentinel is true, right? If sentinel is true, if sentinel is not true, then we need to put it in. But if sentinel is true, we I stay in that position, that j plus 1 position. We don't really move, and we just go on for the next one because these parts will be removed. So we say if not, we're gonna call it sentinel. We call it has seen. Okay, we call it has seen. So if has not seen before, right? If it's not seen before, then presum I shall equal to the current, right? Shall equal to the current, and then we're gonna do I plus plus, right? That looks correct. If has seen, then basically we just put whatever the I position is, and then we just keep going, right? Keep going. If not seen, we put the presum in there. If we have seen before, and then I equal to j plus 1, yeah, and then we move on to the next one. And head always equal to head on next, right? There's no special thing about this. Okay, now we go through everything, and then we can say list node a new head, right? Equal to list node of a new list node, basically. a new list node of pre-sum. Well, it depends, right? It depends where the I is, right? Where the I is. So just say if I, because at the end, I will end at a position, right? I will end a position should be the next position. So if I is equal to 1, right? Then we just return null. It's empty. If not, then we can do oh, this doesn't work. Oh, this doesn't work. You still have to pop. Right? You have to pop. I was going to say you can put a value somewhere. Yo, no, this ain't work, man. This is not gonna work. It will work. Let's make it work. We already invested so heavy on this. Let's make it work. Okay, so this is gonna be 1001 row with 2 columns. Okay, and this is gonna be 0. Okay. Oh my goodness. If this, and then this, and then this hasn't seen. Okay, so we're gonna reset this pre-sum I 0 equal to current, pre-sum I 1 equal to head.val. Okay, and then I plus plus. So if I is otherwise, we set new list node, right? Val shall be pre-sum 1 1, right? Now we say for now while for int j equal to 2, right? We start from 2. J smaller equal to I. No, smaller than I, because it cannot reach I. J plus plus, right? And then we say list node equal to new head, right? And then we say node.next equal to new list node. The value shall be pre-sum j 1 node equal to node.next. Okay, so now we go for the next one. Node.next equals to this, so we're going to hit node.next equals in 2. We hit the last one. Node.next equals to this. Node equal to this, and then we get out. Then we're going to return new head. All right, let's take a look. Let's see how this one goes. My bad. That should be 0. Yeah, I don't think this is gonna be faster though. It's the same. It is exactly the same. Oopsie doozy. Alright, now I have no idea. How do we make this even faster? We have to check the solution. But before we do that, let's take my beloved Rosie. Rosie should have a wonderful, lovely dream. A cute, gorgeous, beautiful, sweet tomorrow for me. Full of energy. I'll be there so many people. Let's continue just a little bit. All right, just a little bit, continue. Let's take a look. A column Owen squared. I thought my method is ON. Yeah, it is ON. O2N. Yeah, you go twice. I think this is the way that we're doing, right? Yeah, it goes twice. Yeah, it is. I'm not sure why it takes so long, but it's all right. 2019. That was a long time ago. That's the problem. Okay, so for this, now we use the sorted lists. So we have to take a look, see what other methods are there. Set with delay, upper bound and set, heap queue and union find. Wow, so many different methods. A multi-set. What's a multi-set? A tree set. I think that's the thing. That's the one that can maintain the order, right? Okay, we'll have a set or insert upper bound. I think this is to find the one that's probably ceiling, S star ceiling, S star floor. Yep. Which means this is a solution. Upper bound. So yeah, in Python you have to segment tree. Heap queue. All right, let's take a look at this. I mean, sorted list is definitely the official solution because in C++ they're using the set, and in Java they're using the tree set. Basically, it's the same thing. It's like a black red tree. It's just self-balancing. It's a self-balancing tree, so you can do insert and remove, maintain the ordering all log n. time. And in Python, you have to use sorted container. But this is something different. This is a min and a max heap. That is interesting. So we are sorting it first based on the values. Okay, so it goes small to large. And then what we do, we get a value, get an index. And I'm gonna push, so the left is a main heap. The right heap is a max heap, okay? And then what do we do? Because of sorting, everything in either heap is already less than val. Ooh, damn. I did not realize that because you already sorted, right? You already sorted. So everything in the heap is already less than value. So you can find the minimum that's less than your value. And you can find the maximum that is less than your value, than your current value. And the max is probably the one you're looking for, right? The max one is probably what you're looking for. And heap left we use to check whether the current number can be the front half. What is that supposed to mean? Front half. Well, first of all, it has to be heap left, and heap left, oh, that's 0. Is this right? Yes, it's correct. Because that's the index. So, right, so this is the index. Wait, hold a second. Why are you doing index? Smallest indices pop off. Oh, wait, hold a second. You are not doing value. You're not doing value, you're doing index. What? Wait, I thought you're doing the value. Wait, hold on. You put in the index, so that's the smallest index, right? Okay, that's the smallest index. That is the biggest index. Oh, that's what it means by look on the left side and the right side. On the left hand side means it's on the left. And they're all smaller than you, right? They're all smaller than you. Then you look for something on the left hand side and you check. If it's smaller than this, which means it's on the left hand side, okay, and it's on the most left, right? Basically it says it is on the most left, the leftmost, and then we just try it. Okay, we just try, because every time we try, it's guaranteed to be the minimal because we sorted already, right? We sorted already. If we have sorted it, then it's gonna be one of these values, right? It's gonna be one of these values. So we check and then we pop, because we are always checking their distance with the closest valid partner. Oh, this is important. We are allowed to I mean, this is okay. I can do that because I'm basically just popping. I'm just checking with the smallest index on the left, so that's the maximum, or the max on the right, right? Which is this plus x is smaller or equal to minus index, right? Minus index is the current index. So we need to make sure that We use to check current number can be the back half. Wait, is this minus x, this minus x is larger equal to index? Yes, right? So we check for both. If it is, then we have a valid, right? We have a valid value. And then we use its difference, right? We use its difference. And we can pop these off because we are always checking their distance with the closest valid partner. Closest valid partner. Okay, let me try to understand that again. We can pop them off. Like if it is valid, right? So we are at a current value, and then we find something that's valid. And because it's sorted, so if we have something valid on the left and in the sorted nums, then that one must be the minimum. If it's possible, then it's the minimum. And if it's not possible, which means if it's not within range, we don't pop it. Okay? We do not pop it, because every time we pop, we try to pop the max distance, right? We try to do the max distance. And if the max distance, there's one that exists, then it's guaranteed that that is the smallest because it's sorted. Because for the current one, if we don't use whatever we have now and then we wait for the later one, then this distance will be even bigger. Beautiful. Beautiful solution. Absolutely beautiful. Absolutely beautiful. All right. I don't want to do it today. So tomorrow, yeah, let's hit this tomorrow. I mean, sorted container is easy, but this is really good. It's very good. I want to think about it tomorrow again. All right, that will be it for today, right? Yeah, that will be it. I will see you guys tomorrow. Adios.